All right, similar polygons is our first topic for today. And similar basically means that the things are the same shape, but might not be the same size. Might not be, meaning they could be the same size. So if they're the same shape and size, we call those congruent. But if they're not the same size, then they're definitely just similar. So you know those questions about is a square a rectangle, is a rectangle a square? We can do that same thing with similarity and congruence. So probably watch for some of those problems. So what are similar polygons? Figures that are similar have the same shape, but not necessarily the same size. That seems darker than normal to me. Figures that are similar. Got a place to define similar? Figures that have the same shape, but not necessarily the same size. That's what similar means. Same shape, but not necessarily the same size. So when we think of angle measurements and segment lengths, which do you think has more effect on the shape? Which do you think has more effect on the size? Angles or size? Which one do you think affects the shapes, the figure's shape? Angles more? What do you think affects the sides? That'd be more the length of the sides? Okay. I would agree with you. Okay, so those two triangles are similar. They look like they're the same shape, same kind of triangle, but they're not necessarily the same size. One is bigger than the other. On the right-hand side, again, I've got two triangles, but those are not similar. That looks more like a right triangle. A right triangle instead of just an isosceles triangle. So just because they're triangles doesn't mean that they're the same shape even. Definition of similar polygons. This kind of looks like a theorem or a postulate, but it's actually a definition. You've got a space there for a definition of similar polygons, not just figures, but now polygons. So this is in detail about the sides and the angles that you were just telling me about. Two polygons are similar polygons if and only if their corresponding angles are congruent and their corresponding side lengths are proportional. The angles being congruent, that's what's going to give the shape. So you have to have angles of one figure congruent to the same angles in the other figure. That would give them the same shape. So corresponding angles are congruent. Corresponding side lengths are proportional. Proportions, those are ratios that are equal. So when we look at the sides, we're going to have to set up the ratios because they're not always going to be the same length. So what ratios would we look at here? Maybe we would go 6 compared to, and I've got to look at the angles. They won't always be sitting in the same orientation. They might be turned or flipped. But 6 would be compared to 12, which is 1/2. 5 would be compared to 10, that's 1/2. 4 to 8, 1/2. 5.4 to 10.8. How do you reduce something like 5.4 and 10.8? When there's a decimal in the fraction, how can we get rid of that decimal to reduce? Multiply by what? 10. Multiply by 10 would be like moving the decimal over. And if you're multiplying by 10 on the top and 10 on the bottom, you're multiplying by 10/10, which is just 1. Doesn't change the amount of it, it just changes the way it looks. So yes, doing something like that, 54 out of 108, then you can reduce more easily. So all of the ratios that I mentioned reduced to be 1/2, so that's what the R proportional means. Ratios that are equal. All of those are equal, so the sides are in proportion. So as we go through some problems, you're looking for angles that are actually congruent, but sides that are in proportion. Now, on that last screen, I had the similar figure, or the similar symbol. We have used that tilde for probably about 4 different purposes now. You think where all we have used that symbol? Congruent. Where else do we use it? Okay, things like contrapositives and that, what did it mean at that point? When we did this. It meant like not P or negation of P, right? We didn't use this a lot, but we do when there's 2 of them together. What does that mean? That doesn't mean it's similar. One of them means it's similar. Used that probably a lot over the years. About or rounded, it's approximately, that's what that means. Okay, so you see that symbol a lot for different reasons, and in combination with some other things, it means different things. All right, multi-purpose symbol. All right, let's identify the pairs of congruent angles and the corresponding sides. Okay, identify pairs of congruent angles. So angle N is congruent to angle Q. Angle P is congruent to angle R. Angle M congruent to angle T. Support. Third angles theorem. Correct. That would be the easiest one to come up with. You could go through the triangle sum theorem, but third angles theorem does it right away. Okay, so our angles are congruent. Now we want to talk about the sides. Is side MN congruent to side QT? No, it's not congruent. It's similar, it's corresponding, the proportion idea. So how are we going to write this down? The sides are proportional, it said. So MN over QT will equal another ratio. Okay. Yep, it is 2 over 1. I guess I was going to do the numbers after a bit. I'll write it down below. 2 to 1. Okay, what's another pair of sides? NP compared to QR. And that would be 1 to 0.5, which would be like 10 to 5. So that's 2 to 1. And then MP compared to RT, that would be 2.2 compared to 1.1, 2 to 1, or maybe I should write 22 to 11 to start with, 2 to 1. So I did get 2 to 1 for every ratio, so here's my statement that shows that they are proportional. Proportions, ratios that are equal. So you're not really using the symbol is similar to, you're setting up the actual ratios. What would you write for is similar to? You would name the whole thing. Triangle MNP is similar to triangle TQR. Is that the right order? So that's where you would use the similar symbol. All right, grab your marker board. Identify the pairs of congruent angles and corresponding sides. What angles would be congruent? And write that proportion statement like I was emphasizing on the last. check to see if they are equal, and then turn it into a proportion with the equal signs. This will be kind of hard for me to check just real quick, so don't erase it right away. I see something you're writing wrong though. Is segment BA congruent to JG? BA the same length as JG?
Oh,
Yeah, so that's not sure. Ratios. These angles, which are not making ratios. And since ratios are numbers, we don't do congruent. That's just the equal sign. Ratios that are equal. It's proportional. I'll show you the answer just a little bit for you to check it. This we're going to clean up and we're going to write in a fraction. BC over GH equals JG over AB, which equals AC over JH. So what you're writing on the page are ratios that are equal is what a proportion is. Okay, here's what I've got. Those are the angles, and then at the bottom, I checked my ratios. Each of them reduced to be 2 to 1. So then at the bottom, I made my statement of proportionality, basically. The corresponding sides in the ratios that are equal. Looking through that, you could have that bottom statement completely upside down. You could have one fraction shuffled, you know, a little bit different variation. How many of you think you have that right? All right, similarity ratio is the scale factor. You know, that 2 to 1 that you were reducing, that is then called the scale factor or the similarity ratio. The similarity ratio is another quick definition there. A similarity ratio, also known as the scale factor. We'll interpret it more as a scale factor when we look at the second part of today's lesson, dilations. But the similarity ratio is the ratio comparing the lengths of the corresponding sides of two similar polygons. The ratio comparing the lengths of corresponding sides of two similar polygons. It really doesn't matter which ratio you use to figure out the similarity as long as you're matching up the sides correctly, because all of those ratios reduce to be the same. If the directions to a problem just say give the similarity ratio, there's actually two answers I'll accept. Either 1 to 2 or 2 to 1. It could be reversed. But if it says give the similarity ratio of triangle ABC to DEF, they're stating what order it should go in. So there's only one correct answer there. So they wanted the triangle ABC first and then DEF second. So that answer would be 2 to 1. If they asked it in the other order, then it's going to be, all right, I said that wrong, 1 to 2, 2 to 1. So be careful, read those problems to see if they're stating the order for the ratio or not. If they don't state an order, I'll accept two answers. Let's reduce though.
So we can leave it, we can put it in a fraction for both.
Yeah, you can give your ratios in fractions. Just don't say that this bottom one is 2. We want a ratio, so 2 to 1. Okay, but written as a fraction would be fine. I just showed you a different version. All right, so similarity ratio is comparing the sides and just reducing it down. I picked 2 equilateral triangles there to make it real easy. Okay, let's try. I think I already said that. When you do that similarity statement, you have to match it up in the correct order. Okay, determine whether these rectangles are similar. If so, we're going to do some things. So what do we need to look at first? We need to look for corresponding angles that are congruent. We need to see if the sides are in proportion. So angles. didn't give you any. Did I? Okay, I said they were rectangles, good. So the angles are 90, 90, 90, 90, and then over here, 90, 90, 90, 90. No matter which angle you look at, it always has a matching one, correct. Okay, how about the sides? Should I compare 6 to 6? Why not? It reduces nicely.
They're not corresponding.
Okay, because of how they're positioned, or is there a different reason? If I turn that second one this way and made it 6 and 4, now would I compare 6 to 6? Okay, no. You need to compare longest to longest, shortest to shortest. So longest here is 9, shortest on that one, or longest on that one is 6. Shortest on the first is 6, and shortest over there is 4. So we need to reduce those and see if they're the same. 9 to 6, divide by 3. 6 to 4 reduces to, we divide by 2, can't you? So I get 3 to 2 for each of them. Now technically I probably should look at this bottom side compared to that bottom side. Still same thing. And this side compared to that one. You really do have to look at all sides. Do you want to go get a drink?
Yes.
Okay. All right, and I'll tell that she's needing that. Okay, so technically you are testing all sides because you got some that are equal there. Okay, so I think we got a similarity figures. So yes, they're similar. Now what do we need to do? Write the similarity ratio of the first figure to the second figure. Is that what I did here? Was this first figure to second figure? Yes. It wasn't this 6, it was this 6. I was comparing these two, and I was comparing these two. So evidently my similarity ratio then, when I reduce it, is 3 to 2. And a similarity statement. Do we have a symbol for rectangle? It's parallelogram and triangle. Otherwise, we could write it out, or I'm just going to put A, B, C, D. Is similar to E, F, G, H is probably the easiest matching, but it could also be G, H, E, F, or F, E, H, G. These rectangles could be turned different ways when you're matching it, flipped over, things like that. So there's multiple matchings to that one. But that's what the similarity statement is, naming the figures in the order they match. Okay, probably have another one like that for you to do. After I click through this solution. Whoops. Okay, there's a couple triangles for you to look at. Determine whether they are similar, and if so, I've got some things for you to do. So check out the angles to see if every angle has a corresponding congruent angle. Check out sides, see if they're the same ratio.
Do you need one of my passes?
Now everybody's getting coffee. Alright, are they similar?
What?
Can you convince me?
Do you remember the pile you sent me? Yeah. Yeah.
Okay, she's saying do the isosceles thingamajig, whatever that is.
Do we know there are sauce? Oh, yeah, we do.
180 minus 36.
Okay, so she's finding the other angles. Okay, find the other angles. So yes, you do have some base angles that are congruent. Well, what was 180 minus 36? and then divide by 2. What's angle P? 72 degrees, 72 degrees. And I don't know if I even need to find the angles in this one because there is no angle in that triangle that would match with the 62. So right now I know the angles are not the same, so they're different shapes. Are they similar? No. Now you would have had problem checking out the sides anyway. Because I know I have 10 to 5 and 10 to 5. How about PR's length and SW's length? Notice those weren't even given. So you can't make sure all sides are in proportion if you don't have those last two measurements. So a couple problems with that one. So that was not similar. How about these two? I didn't give you specific angle measurements. Can we still make a determination on the angles? Two angles are the same in each one. Is that enough?
No,
They're not corresponding. If I think about this one turning counterclockwise, 1/4 of an inch, you mean corresponding as in they're not sitting in the same position? Okay, corresponding doesn't mean they have to be sitting in the same position, just that there would be a matching one. So if there's a right angle here, does the little one have a right angle? Yes. Angle L is marked with 1 tick mark. Does the little one have a 1 tick mark to match it with? Yes. How about angle J? It is congruent to angle S? Convince me? Third angles theorem. Okay, so although it's not marked, angle J, third angles theorem is congruent to angle S. So the angles make it through. Sides. In proportion? Check out the ratios. Which sides would you compare? If you pick the easy one, 75. The hypotenuse would be compared to 30. Okay, then 60 would be compared to not 18. Look at what angles 16 is between. Or 60 is between the right angle and the single angle. So that would actually be the 24 over here. And the 45, the shortest side of that triangle, would be compared to the shortest side of the other triangle. And again, look at what angles it's between. So corresponding doesn't mean in the same orientation position. They don't have to be turned the same. Reducing. What's that reduced down to be? 5 to 2, that's reduced, dividing by 15, I think. 60 and 24. Dividing by how much? 12, you said? Okay. 45 and 18. Or 2, that's dividing by 9. Okay, so all of those ratios ended up the same. So it sounds like we're getting a yes, that they're similar. So what do we need to do? Similarity ratio of the first figure to the second. Is that what we were doing? Okay, yes. Now, if it wasn't what we were doing, then we would have to just turn it over, get it to be the right one. Okay, and a similarity statement. If I call the first one triangle LMJ, is similar to triangle, what matches with L? P, and M with, and J with S. So P and S. Chris?
So the way you orient your ratio doesn't matter.
No, as long as you're consistent. I mean, if I went big figure to small figure for the first one, I can't switch this to small and big. It'll never be equal. So be consistent which figure's on top and which is on the bottom. The only time that really the order mattered in that one was when the question asked what the similarity ratio was of first figure to second. That had a definite order to the answer. Okay, let's go on. Okay, and that's what we were just talking about. Be sure that you match up the corresponding measurements. So in a real life kind of situation, find the length of the model car that is similar to the race car to the nearest tenth of a centimeter. I'd say the details on those cars are not the same, but they're using it as an example where you can do ratios. Let's see what the length of that model car is. If it's built to be similar to the race car. Compare matching things. Okay, so think what some of you were asking on homework. Let's see if you can actually compare the matching things. So the length of the race car and the length of the model will be in one ratio. The width of the race car and the width of the model in another ratio. How are you setting yours up? How are you setting yours up? Okay, so the width to the width. 5 meters over x. Now I was writing the units because that's going to help me figure out what the units will be on x. Looks like in the first fraction I'm comparing meters and centimeters. So in the second one, meters, and x is going to come out with a centimeter type of unit on it. That being the case, you can forget what those actual units are when you cross multiply. 1.8 times x equals 6.3 times 5. 6.3 times 5 divided by 1.8. 17.5? What kind of units? Centimeters. We're going to try and pay more attention now to labeling units as we're getting into things that are figuring lengths and areas and surface area and volumes.
Why wouldn't you change the meters to centimeters?
You could.
Wouldn't that?
Okay, let's see what happens. How would you change this meters to centimeters? How many places? How many centimeters in a meter? Centa, century, 100. So it'd be like multiplying it by 100. So that would be 180 centimeters. The bottom would just stay 6.3 centimeters. Okay, this fraction would become 500 centimeters over x. Okay, so all I'm doing is trying to see if it made any difference. So if you take 180 x equals 500 times 6.3, you multiply that and divide by 180, you still get 17.5. Okay, so notice it really didn't matter because when I do this fraction, if I would divide this one back by 100 and 100, that would be like leaving this at a 5 and that at a 1.8. So you're doing the same thing, really. So you didn't have to change the units, is the point of what she was asking. As long as you are using the same units in both ratios. Okay, let's try, I think I have one more of that type after I get through that solution. Okay, a train boxcar has the dimensions shown, 9 feet tall, 36.25 feet wide or long. The model of the boxcar is just 1.5 inches wide, I guess. That must be a top view, what I was doing. Figure out what the length of the model would be. I was thinking it was a side view, but it's a top view. So that's the width and the length of each car. take note of the units to make sure you're comparing the same units on each ratio. And then the units don't have to be used when you're doing the mathematics. This was the length of it. Let's compare that to the length of the model. The width of the boxcar. So you're comparing length to length, width to width. Okay, now what we can do is cross multiply. This number times that one.
You know you put in, do that. Yeah, that's right. And then you cross multiply and divide by the other one.
I like it.
Okay, and answer comes out to be
5.05 and 7.
to the nearest inch? 5. Nearest inch, they just wanted it rounded to 5. Question on that sample.
Did I do it right? Why did I erase it?
You had it?
Yeah, and I erased it.
Okay. Are these two polygons similar? No? Why not?
Angles.
Okay, the angles are not the same, so the shapes are different, correct? Notice the sides would have been in the same ratio, but it's the angles that made the shape. Yeah, rhombus compared to a square, not the same shape. Okay, this is similar to what we were just doing, but presented a different way. It says the ratio of a model sailboat's dimensions to the actual boat's dimensions is 1 to 30. So the 1 is the model length, the 30 is the actual. They didn't say whether it's feet or inches because you could apply it to any measurement. Okay? If the length of the model is 10 inches, what's the length of the actual sailboat in feet? Model 10 inches. Would that be the numerator or denominator of the second fraction? Numerator, because it's the model. And the first sentence said the model came first. So we'll set up what you would cross multiply. What over what equals what over what? 1 over 30 equals, you can calculation quickly. 1 over 30 equals 10 over what? X. So then you're cross multiplying, what do you get? 300? 300 feet?
300.
300 inches is what you got, right? Because you didn't specify any different units here, so 10 inches, it's 300 inches that you just found.
25 feet.
How do you get that into feet?
Divide by 12.
Divide by 12,
25.
because 12 inches in a foot, 25 feet. You'll have to do some converting now and then. And the next one's kind of an opinion here, a correct opinion. Tell whether the following statement is always, sometimes, or never true. And I'm going to have you get up and go to the corner of your answer. Okay? So we'll go always is that front corner, sometimes it's back there, never is there. Okay? So always, sometimes, never. Got your answer?
If they're
Okay, move.
okay,
Goes in order from that corner. Always, sometimes, never.
if they're exactly the same, are they?
You'll have to decide.
Yeah, but the English. Okay, the first one is sometimes.
You're the nevers.
Oh, wait.
Sometimes-
Sometimes it can be wrong.
Yeah, Grace is so wrong.
You're not supposed to do that. Oh, that's true.
All right, we got somebody everywhere.
Just because.
You're never.
Did he point out something that you hadn't thought of?
Are they similar if they're the same? No.
If they're congruent, are they similar is what the question is.
Really have any.
No, it's the other way.
Okay, are you where you want at the moment? Okay,
Can I go to that corner?
can't move right now. All right. Let's see, equilateral triangles. Equilateral means? Equilateral means all sides equal. Which also in these figures means all angles are equal, which is 60 degrees?
Yes.
Okay, so the angles are all the same. 60, 60, 60. Okay, sides. Okay, what if I throw a 10, 10, 10? 5, 5, 5. Ratio 2 to 1, 2 to 1, 2 to 1. Okay, some of you were asking, what happens if they're the same? What if these were, I know it doesn't look the same, but what if it was 10?
The 1-to-1
The
ratio.
ratio would end up reducing 1 to 1, 1 to 1, so they are in proportion. So the correct answer was,
Oh, wait. Yeah.
all right, have a seat.
Riley's like, you want some more? She just be the one
Riley looked at it, this was the shortest distance to walk.
I know, I noticed that.
But she was good to stay there by herself.
Riley.
Okay, to finish up, I wanted to tie the 7-6 briefly into that, so I think it's on the halfway down on the 7-5 page. Oh, probably not. We might use the graph paper part. Well, we might use the graph part actually. Okay, we're gonna just do a little bit of applying similar properties in a coordinate plane, looking at if you were graphing something, could you graph a dilation accurately? What's a dilation? It's a transformation that changes the size of a figure but not its shape. So basically it makes a similar figure. Changes the size of it but not the shape. The pre-image and the image are always similar. Pre-image is what you start with. It's halfway down on the 7-5 page. Pre-image is what you begin with, and the image is what you're going to draw. You will need some graph paper for your assignment. There are some simple diagrams that you're going to draw that are either bigger or smaller than what they were as given. The scale factor, just like we talked about the similarity ratio, the scale factor describes how much the figure is enlarged or reduced. How much is it enlarged? Is it enlarged with a 5-to-1 ratio? What would that mean? 5-to-1 enlargement. It's going to be, every side measurement is going to be 5 times what it was originally. So it's going to enlarge it 5 times as much. If it's reduced, maybe you're going with a scale factor of 1/3. So it's going to shrink it down to 1/3 of what it was. So what are we going to do? That bottom part tells us how we're going to calculate our new points to graph. For a dilation, if the scale factor is k, that's just kind of a standard they use for scale factors, you can find the image of the point by multiplying each coordinate by k, the scale factor. So we're going to take an ordered pair, a point on the pre-image, the figure that we're given, and we're going to multiply each coordinate by the scale factor to get the image of the new drawing. So if the point was 0, 5, and we want a scale factor of 5-to-1, multiply 5 and 0 times 5, it's going to now be be at 25 instead. So it's gonna go higher or lower, wider than what it was. Done with the screen? All right, so if you want information about is it an enlargement or reduction, an enlargement, the scale factor is going to be bigger than 1. A reduction, thank you, the scale factor will be less than 1. So if the number we're multiplying by, if the scale factor is bigger than 1, it's an enlargement. Good information for you. If the scale factor is less than 1, it's going to make a reduction. It's going to make it smaller. That's the number we're going to multiply all the coordinates by. Okay. Now I've just given you some real simple, just rectangular pictures. You probably can't even tell what that is until we enlarge it. It is a horse of some kind. Okay, we are going to figure out what the size of this picture would be after a dilation with a scale factor of 5 halves. Will 5 halves enlarge it or reduce it? Is 5 halves bigger than 1 or less than 1? Bigger. So your notes just said if the scale factor is bigger than 1, it's a reduction. Enlargement. The scale factor is bigger than 1. You're going to multiply it to make it big. Okay, so let's take the points. So write down these points. 0, 0, that's A. So A is 0, 0. B is 0, 4. C is 3, 4. D is 3, 0. Okay, now multiply each of those coordinates by 5 halves. If you don't like it in fraction, 5 halves is the same as 2.5. So multiply every number by 2.5 and write down what those new points will be. What's A prime going to be? What's B prime going to be? Multiply each of the numbers by 2.5. Multiplied, get A prime to be 0, 0, B prime to be 0, 10, negative 7, excuse me, 7.5, 10, and then 7.5, 0. Okay, so those are the new points. Here was our original horse picture. Then when we enlarge it, this was the original. It gets this much bigger when we did the dilation to make it bigger. So now what it is there? I think that looks so dim. Look better.
What is it?
It's a cow, it's a chocolate cow.
It's a chocolate cow with a long face and pointy ears
Whatever.
and nays.
Does it look like the area would be 2.5 times what it was? If you take 2.5 of those gray spaces, will that fill the whole picture now?
About, yeah.
I don't think so. It might fit
4 to the
maybe
4.
half of it. It's like, yeah.
Yeah. What?
Okay, what's this one?
It's 0.5 smooth. A surfer dude.
A surfer dude. Okay, we're gonna make a scale factor of 1/2. Will that make it bigger or smaller?
Smaller.
Smaller, and since we're running a little short on time, everything times 1/2 would make it go down to that little picture. Now, the other type of problem that is on that assignment is just something like this. You're gonna try and find the coordinates of U and then the scale factor. What you're looking at here, if you can just bear with me a little bit here. What you're looking at is just two similar triangles. Up to S, that is 16 units, look at the graph. To R, it's 12 units. Up to U, I don't know how far up to go, but on this side it's 9. Why am I not putting it as -9 and -12? It's a distance, you don't do negatives, okay? So ratios to find the missing side. And I think when you do that, you end up with Y being 16. So the point directly up from the origin was 0, 16. And the scale factor, notice the order that they're asking it. So that would be like 12 to 9, or, oh, that's not 16, is it? 12. I was trying to remember from last period what it was. Got the wrong number. 12. I knew it was a duplicate of something. Okay, or 16 to 12. So you can reduce the scale factor. So you're getting the scale factor from the sides of the triangles. I'll give you just a quick preview there. You're doing the triangles of similarity. All right, let's call it quits there with this assignment. Remember, I did put assignments on eBackpack so you can work ahead if you need to. 465. Let's see, wait a second. That's not the right one. Gotta read the right one here. I'm trying to go fast and I'm looking up. 9, 20, 5, 8. They're short problems in the most part. The calculation type go a lot faster. And some of those are just, are they similar or not? All right. I think there's some testing going on tomorrow, but most of you aren't affected because it's juniors. They start their state testing.